let us learn about circuit matrix or cycle matrix of a graph. Let G be a graph. The number of edges in G be E. G has E number of edges and it has got, say, Q number of circuits or cycles. Then circuit matrix or cycle matrix is represented by Bij, which is matrix of order Q cross E, which is again 0 1 matrix, and any entry Bij is 1 if ith cycle includes jth edge. If ith cycle or circuit includes jth edge. Otherwise, the entry Bij is 0. For example, if I have a graph, say my graph is like this, which has got parallel edge, one self loop and one single edge. I'll name the vertices 1, 2, 3, 4 and 5. Name the edges A, B, C, D, E, F and G. I'll name the cycles first. Say cycle 1. This is this cycle B, D, E, G. B, D, E and G. This is cycle 1. Another cycle B, C, E, G. B, C, E and G. And the third cycle, say this one set of parallel edges, they also form a cycle, so C comma D. And the last cycle is a self loop, that is H F. So I am writing circuit matrix or cycle matrix is denoted by B. I have to take cycles along the rows C1, C2, C3, C4 and edges along the columns A, B, C, D, E, F and G. Okay. Now cycle C1 includes the edges B, D, E, G. Okay. If ith cycle includes jth edge, then the entry is 1. So C1, for the cycle C1, it includes B, D, E and G edges. So those entries are equal to 1. B, D, E and G. Rest all the entries are equal to 0. Then cycle C2, it includes edges B, C, E, G. B, C, E and G. Rest edges are not included in the cycle C2, therefore those entries are equal to 0. Next C3, cycle C3 includes C and D edges. C and D, others are equal to 0. Then C4, this last cycle, it's a self loop, so only entry F is equal to 1. I mean, this entry is equal to 1. Rest all zeros. So this is circle matrix for this graph. See, from this we can observe few things when we look at this cycle matrix or circuit matrix. These are the observations which can be made about circuit matrix. First one is a column of all zeros corresponds to a non-circuit edge, means that edge is not included in any circuit. You can observe in the see this column, okay, all the entries are 0, therefore I can say that this edge is not included in any of the circuits. A column of all zeros, column of all zeros corresponds to a non-cycle edge. Non-cycle edge. Any edge that does not belongs to any circuit, for that column vector, that all the values are equal to 0. Remember one thing, each row in a cycle matrix or a circuit matrix is a circuit vector. Each row of, in fact you can denote it as B of G also for the graph. So each row of B of G is a circuit vector or cycle vector. It's a circuit vector. In a circuit matrix, self loop corresponds to row which is corresponding to self loop will have single 1. A row which corresponds to self loop will have only one entry, which is 1. So self loop, if graph has self loop, then the matrix will have, or row will have a single 1. The number of ones in any row which is equal to number of edges in the corresponding cycle. Number of ones in any row which corresponds to number of edges in the cycle. Number of ones in any row is nothing but number of edges in the corresponding cycle or circuit. Then if my graph G is separable or it is disconnected graph, say let it have two components, say G1 and G2, suppose are the components of the graph, then B of G can be represented in block diagonal form like this. This will be the circuit matrix for the component G1. These all the entries will be equal to 0, and this will be the component for component G2. This will be the circuit matrix. So this total diagonal form gives you the circuit matrix for G. If G is separable or disconnected and has got two components, suppose it has got two components, then I can write circuit matrix in this manner. And the last observation is permutation of any two rows or columns in a circuit matrix simply corresponds to the relabeling of circuits and edges. I mean to say, if I name this cycle as C4 and this as C1, then this will be the permutation of any two rows. Okay. Similarly, if I name edges, relabel edges in another manner, then I'm going to get another circuit matrix. So permutation of any two rows or columns in a circuit matrix, if I do any permutation over here, that corresponds to the relabeling of the circuits and edges in my graph. Now let us see how incidence matrix and cycle matrix are related. So let us prove a theorem which states, if I have a graph G which is not having any self loops and matrix A represent incidence matrix and B represent cycle matrix, then every row of B is orthogonal to every row of A. In other words, A into B transpose is equal to B into A transpose, which is equal to 0 mod 2, where B transpose and A transpose are the transposes of matrix B and matrix A. So let us prove this. If I have a graph G which is not having any self loop, and A represents incidence matrix and matrix B represents cycle matrix of graph G. This is my graph G. Okay. Now, for any vertex, say suppose I consider a vertex Vi of graph G, then this Vi, vertex Vi, it may be included in, say, some circuit, say Zj. It may be included in the circuit, or it may not be included in the circuit Zj. There are two possibilities for any vertex Vi of graph G, which may be included in circuit Zj, or it may not be included in Zj. In case suppose vertex Vi of G is not included in Zj, then there is no edge of Zj which is incident on Vi. If Vi is not in Zj, then whatever the edges which are included in Vi, which are incident on Vi, which won't be there in the circuit Zj. So that's the same as saying no edge of Zj which is incident on Vi, which is incident on vertex Vi. Okay, and suppose if Vi is in Zj, Vi is in the circuit Zj, then what happens? There are exactly two edges of Zj which are incident on Vi, because Zj is a cycle. So if Vi is in the circuit Zj, then there will be exactly two edges of Zj which are incident on Vi. It implies there are exactly two edges of Zj which are incident on vertex Vi. So this is the basic thing we can make out by taking the vertex, whether it is included in the circuit or which is not in the circuit. Okay. Now consider I have to prove ith row, any ith row of A, which is it is orthogonal to any jth row of vertex, any jth row of matrix B. Okay. So now consider ith row of A. Consider ith row of matrix A and jth row of matrix B. In fact, jth row of matrix B, which is nothing but jth column of matrix B transpose. Jth column of matrix B transpose. Jth row of matrix B, which is nothing but jth column of matrix B transpose. Okay, I'll consider this now. Since I know that I have defined it in the statement itself, that edges are arranged in the same order, therefore the rth entries of two rows are both non-zero if and only if, say, the edge ER is incident on ith vertex VI and is also included in the jth cycle. I mean, say, in both the case matrix A and matrix B, what we have done is, say, same order, say these are the edges, suppose, in the same manner I have named the columns. Okay, same in this case also, A, B, C, D, same order I'm applying. Okay, so if I consider non-zero entries, any rth entry if I consider in these two rows, they will be non-zero if, say, non-zero entry in this case, in this position, suppose if I consider some rth entry, this will be non-zero if and only if this particular edge is incident on this particular vertex and this particular edge is also there in the particular cycle. Got the point? So I can say that the rth entries in these two rows are both non-zero if and only if the edge ER is incident on ith vertex, say VI, and is also included in jth cycle Zj. Okay, so we know matrix multiplication. When I write a matrix AB transpose, which can be written like this: summation of matrix A, which has got IR and matrix B transpose, I'll write RJ. Okay, I'm taking sum of all these products, okay, summation of these particular entries, which can be written as summation of matrix A with entries IR and B transpose RJ is same as writing BJR, right? So which will be nothing but summation AIR BJR. Okay, so product AB transpose is nothing but summation of these entries. I think these things we know by using matrix multiplication I have written, so I hope you know this. Okay, now for each edge ER we have the following cases. For each edge ER, for each edge ER of graph G, I have following cases. First case is that edge ER is incident on ith vertex and it is that particular edge is not in jth cycle. First case, ER is incident on ith vertex, that is VI, and this ER edge does not belongs to jth cycle. When that is the case, value of AIR, this is in that entry in incident matrix, AIR will be equal to 1. But when I consider the particular entry in circuit matrix, will be equal to 0, because that edge is not in the cycle Zj. Okay. The second case is if ER is not incident on Vi, and I'm considering edge ER is included in Zj, exact opposite of this. In that case, entry AIR will be equal to 0, because this edge is not incident on the vertex Vi, so this particular entry will be equal to 0, and entry BJR will be equal to 1. The third case is ER is not incident on Vi and it is not included in the jth circuit. ER is not incident on Vi and ER is not included in the J. In this case, I'm going to get both the entries equal to 0. AIR equal to 0 and BJR equal to 0. So in these cases, ith vertex Vi is not in jth cycle Zj, and we have got AB transpose with the entries say Ij equal to 0, which is same as writing 0 mod 2. So in these cases, ith vertex Vi is not in the cycle Zj. Okay, and I have got this. Now the last case is ER is incident on Vi and ER belongs to Zj. In this case, I'm going to get two edges, say ER. When I say this is ER is incident on Vi, then there will be exactly two edges, say ER or ET, which is incident on Vi. Because I'm saying this edge belongs to Zj, means there has to be two edges which is incident on Vi. So one, if I take it as ER, and another one I'll take it as ET. Okay, say there will be two edges on Vi, that is say ER and ET, okay, which belongs to Zj, so that we are getting AIR equal to 1 and AI, this I have taken T, so let's use that notation, AIT equal to 1, and the entries BJR will be equal to 1 and BJT equal to 1. Got the point? See, that edge is incident on Vi and that edge is in Zj. When I say incident on Vi and that belongs to Zj, there has to be two edges. I'm taking it as ER and ET. So with respect to these two edges, entries AIR equal to 1, AIT equal to 1. Similarly, BJR and BJT equal to 1. Therefore, I can write AB transpose with the entries Ij will be equal to summation of AIR and BJR, which will be equal to 1 product, no, 1 plus 1, which will be equal to 0 mod 2 or congruent to mod 2. You are getting 2. When you take mod 2, you are getting value 0. Therefore, I can say AB transpose equal to BA transpose, which is equal to 0 mod 2. Or every row of A is orthogonal to every row of B.